Nic Hohn, Chief Data Scientist at QuantumBlack, which is part of McKinsey in Australia. Welcome to the Data Exchange podcast.
Thank you, Ben. Thanks for having me.
So I have a bunch of questions for you, but the first few questions will center around your upcoming talk at the Ray Summit, which I am the external co-chair. And listeners, you should definitely sign up. We have an outstanding program. It's free, it's online, and you can find more details at raysummit.org. But Nic is going to give a keynote, and another colleague of Nic will give a deep dive about this topic that we're about to discuss, which is making boats fly with Ray and AI. So, Nic, so describe to us what was this project about?
Sure. Look, I'll start by describing the project, and then I'll go into a bit more depth about how we solved it. So, the America's Cup is the oldest sports trophy in the world. It's the most prestigious sailing trophy. And so you always have a bunch of different competitors all aiming to win it. And we supported Team New Zealand, who were the cup holders at the time, to defend their next the campaign for the next trophy. And when you think about AI, it's always good to know exactly what you're using AI for. And so in this case, the use case we're trying to solve was based on the team had identified a bottleneck in their development process. Just to take you back maybe a step.
The America's Cup. Nic, here, development means also the physical construction of the boat, right?
Yeah. Development means building a boat. And so each team has about 3 years to go from paper, specifications on paper, to building the fastest possible boat for the next race. And it's not like maybe a traditional organization where you can slip a quarter and there's no big implications. Here, either you're ready on D-Day or you're not. And if you're not, then you're not competing. And so they have a very iterative process to build their boats. And for this cup, they had decided to do all the design using simulation with minimum amount of physical prototyping to reduce costs.
So first of all, is this new?
So it's probably the first time in the cup that they've really pushed the simulation angle so much. In previous versions, they were allowed to have tow tanks or wind tunnels or smaller boats to make and test a lot of their decisions. But this time around, they decided to only use simulation. So in practice, how it works is that you're allowed to build 2 boats, only 2, I would say. And the part of the boat we're mostly interested in are the hydrofoils. So think of underwater wings that at a certain speed will start lifting the boat out of the water so that the boat can go really, really, really fast by minimizing the drag. We're talking speeds of 50 knots. So for the non-sailors here, it's about 60 miles per hour, close to 100 kilometers per hour. And so designing those foils is obviously critical to the ultimate performance of the boat. And they only allowed, in the entire 3 years, they only allowed to build 6 foils. That includes the 2 that you use for racing. So you only get 4 chances to physically build something and test it. So that's why simulation is absolutely fundamental. And so when the designers design the boat and design the components of the boat in the simulator, they have a very good idea of how the boat will react to the wind or to the water. But they need the sailors in the simulator to, if you want, drive that boat at maximum speed so that they can then identify performance issues and any difference in performance. Assuming the sailors are sailing optimally, then any difference in performance is due to the design. And that's what enables them to then change that design.
So quick question, the simulator, is it a common simulator that all the teams use, or is simulator is also a source of IP?
It's an absolute source of IP, which I can tell very little about, actually. If just for the purpose of what we did, it was very much a black box. where you send inputs to a range of controls on the boat. It could be the steering, it could be the angle of the flaps on the wing, or the way the sails are actually managed, and you get back a new state for that boat. But the point I want to make here before we dive into this is the fact that because you have humans in the loop, like we're talking Olympic level sailors, professional sailors who have to get into the simulator, sail the boat, and then give their feedback to the designer. That's the slow part of the simulation. And so what we came up with was a way to not fully remove the humans from the loop, and I'll come back to that, but really enable the designers to iterate at speed on their designs, so that by the time they present a design to the sailors, they know it's very, very good and pretty much optimal. And so all we did was building an AI agent that could learn to sail the boat for a given design at optimal speed.
So this is where reinforcement learning and
Yes.
Ray RL-lib come in. So how hard was it to take that problem and map it into the reinforcement learning context?
Very hard. You see my hair's getting gray a bit on the sides. I'm losing a lot. I've lost a lot in the project. It was immensely complicated and very with a very uncertain outcome as well. But that's what made it really exciting. You know, those teams, they're pretty small teams. And so they only have the bandwidth for one or two science experiments through the 3 years. And that was one of them that they decided to go after. And so, yeah, from a reinforcement learning perspective, I would say you need three things. First one, you need to know what good looks like. So you need to have a good reward function in your system. And I'll come back to that because that's probably the hardest.
That's very hard, yeah.
Yes. The second thing you need is access, obviously, to a very good simulator or digital environment with which the agent can interact. So that was the simulator that Team New Zealand had already built. As you can imagine, we had to make a few changes to enable it to run at scale on Ray and things like that. We'll come back to that. And the third one is obviously access to enough compute power. And that's where the cloud solves that problem. But yeah, so extremely hard, very iterative. And, you know, maybe if I just want to highlight one challenge, I mentioned, the reward function, trying to capture from a subject matter expertise perspective what sailing optimally means for those Olympic sailors is really, really tricky. And it's not something that you obviously get right the first time, and you do a lot of iterations, but you have so many moving parts because you have your reward function that's changing. You don't actually know for 100% whether your learning algorithm is the right one and whether it's actually learning what it's supposed to be learning. And so when you don't get the right answer, it's sometimes quite hard to know what to fix and what to try again and iterate. But ultimately, we managed to build an optimal sailing agent that could then be used to quantify the performance of those different designs.
So without giving out the details, how much compute are we talking about here in terms of doing some of these simulations and optimizations? Are we, so is it yeah, so what kind of scale are we talking about?
Yeah, so scaling wise, definitely we use the cloud. We were on AWS, and at times we would have maybe 1,000 simulations running in parallel, each of them requiring specific GPUs to run. And you know, this type of workload is highly variable. You'll have periods of times where you're learning a lot and you need a lot of compute, and other times you're analyzing the results and you need no compute. And so a lot of the challenges we faced here are very much related to almost what you could call computational debt, where you're fundamentally trying to solve for the most sample efficient algorithm you can find to learn what you need to learn, but without wasting compute. So we spend a lot of time on the sample efficiency of the algorithm. We also spend a lot of time on accessing the cheapest compute. And that means having a system that's resilient, that can run on spot instances, for instance, with all the complexities when you're trying to save the state of your RL algorithm and suddenly you lose a node, and what happens then. And the third one is also emphasizing the fact that the algorithm that we use, we try to make it as generalizable as possible. So in our context, that means that you don't just learn to sell one very specific type of boat with one design of foils, but you have one algorithm that can actually optimally sell a range of designs. So you don't need to train it for every single new design.
So it sounds like, this is a lot of what you described is precisely in RLlib and Ray's sweet spot. So it sounds like the timing of this project coincided with kind of like the availability of Ray.
Yeah, so just to give you maybe a better timeline, we actually started this project middle of 2019, like quite a long time ago, if you think about the Ray releases since then. And so we're talking about version 0.7 at the time, with a lot of challenges. And you know, when you start this style of project, you try to do a very quick but efficient due diligence on what framework you can use, and you look at different frameworks, then you pick one and you realize there were problems, and then we landed on Ray. But the earlier versions like 0.7 or even 0.8, I think, were quite limited in certain aspects. And for us, the main challenge at the time was really the learning algorithm. We landed on SAC, but at the time, the version that was in Ray just didn't work for us. So we actually re-implemented our own version of SAC to be able to tweak a lot of things on it, like the way you manage the replay buffer and the way you initialize the system. But yes, Ray proved really valuable in managing those very large scale clusters.
Yeah, fine-grained resource management, right?
Very fine-grained. And sometimes actually it's a problem because you get access to so much fine-grain that sometimes you would love to not have to make certain decisions when you start. After a while, it's great to be able to really fine-tune, for instance, the exact amount of CPU and GPU that should be allocated to a given learner, for instance, especially when you do things at those scales, where every efficiency becomes really important. The aspect of Ray that we also use quite extensively was Ray tunes. Obviously, you know, when
I'm a big fan.
Me too. When you think about this type of project with so many degrees of freedom, there's a lot of hyperparameters that you want to be optimizing within the way that your agent is actually learning, and that's where that becomes really important. The second aspect in which we actually use RayTune was also to manage what I would call reproducibility, making sure that when you run your RL algorithm, fundamentally you're doing some form of optimization. It's making sure that every time you run it, you get the same optimal solution. Because obviously, reinforcement learning in general is well known for not being so robust. Right. And you can be running the same thing twice and getting very different results. And you know what? In a lot of situations, that's probably fine. In a lot of like traditional AI use cases where you need to capture some value, but not necessarily everything, maybe that's fine. Here, because we're talking competition, we're talking marginal improvements, you want to make sure that you're capturing every single amount of performance from the system. And so to do that, you really need to make sure that every time you run it, you get an optimal solution. because you end up comparing performances between designs that are so close to each other that you want to make sure that the noise in your reinforcement learning system is obviously smaller than the difference in performance between those designs. And so that's what we use Ray as well, to just run very large scale experiments across dozens of seeds, for instance, to make sure that the system was stable.
So with this project, at what point did you get the sense that, hey, this is more than a science experiment? We may have something here. At what point?
No, that's a good question, because there was certainly a lot of uncertainty at the start. You know, in a lot of traditional AI projects, you end up working with clients who don't always see the value of AI. And so you have to convince them that there's value in doing things a certain way. Here with Team New Zealand, the team was so technical, they knew right from the start there was a huge amount of value in doing that. Where they had more questions was on the feasibility, on like, okay, look, great if we can do it, but this is highly uncertain and it's not clear how to make it feasible. And so it took a long time, it took months, but I guess the key point here is that you wouldn't want to use reinforcement learning when you're first trying to solve a problem. I think it works best when it's a problem you've already tried to solve, maybe with more traditional optimization techniques, and maybe found some limitations, either in performance or in convergence or in something else, so that you already have a good idea of what you're solving for. And you also have a bit more of a baseline of what good looks like, because one issue with reinforcement learning is that it's such a big black box that you run it and then you get an answer, but it can be really hard to identify whether that answer is good enough or not. So Team New Zealand had done a lot of optimization work as well, maybe more traditional optimization, which works very well in more static regimes, like for instance, when the boat goes in a straight line. And what we brought is the ability to optimally control the boat when it's turning, for instance, where you have a very complex sequence of maneuvers and actions to take. But so to come back to your question, we knew we had something working when fundamentally we were as good or better than the sailors. That was the benchmark we were aiming for. So we're talking Olympic level control of the boat. Anything below that was not going to be good enough. Wow. So the bar was really, really high on that one.
So now that you finished this really complex problem involving reinforcement learning, and I've been thinking a lot about reinforcement learning in the context of traditional companies and traditional problems. And last year, when I did a bit of a digging, what I found was, okay, so there's some applications in recommenders and personalization, but they tended to be limited to tech companies, so some really advanced tech companies. So more recently, I kind of so I've been doing a study of Fortune 1000 companies, and what I found was, okay, so it's still early, quite early compared to say something like deep learning, but there are some initial signs even outside of tech. So here's what I found. So finance, so there's some people talking about trading. Chip designers, I guess that's technically still part of tech, right? So the people who use simulators to design tech. So I guess other companies outside of tech are using it for personalization and recommenders. So Starbucks, Nike, and some other retailers. And I think some of the auto companies are using it in terms of self-driving cars or as part of the self-driving car development process. Cybersecurity is another realm, and so on and so forth. But so, Nic, with that said, so what are some of the key ingredients of a problem that would lend itself to RL, or would you basically talk people out of using at this point?
No, look, I think it's a really good question. I think it's the right way to frame it. Like, you need to have the right circumstances for RL to be the right answer, as opposed to make it RL the answer to any type of problem. And so in my experience, some of the key ingredients are highly complex optimizations, usually involving a sequence of actions over time. I think RL is really good when you only learn the consequences of your actions even further in time. So in situations where the reward might not actually be instant, for instance. And so keeping this very broad lens, I think the examples you mentioned, I think are very interesting around any kind of very complex and dynamic operations. It could be dynamic supply chains, or it could be next best action models, or complex optimization of a telecommunication network where your needs will vary depending on how the users are interfacing with the network. And so I think in all those situations, again, I think I would strongly advise against using RL as the starting point. But if you find that traditional techniques are limiting, it could be limiting in many ways. It could be that you need a lot of heuristics in your optimizations to make it converge. Or it could be that you can only run it up to a certain scale and then your optimization no longer works at all, for instance. There's many reasons why you might want to go further, but you do need to do that hard work first so that you have a clear idea of what you're solving for, you have a good idea of your optimization function, and then you bring in the RL technology. And I think in terms of the barriers to entry, as a lot of the challenges we see currently are really around getting access to a good simulation environment. RL right now only works if you have simulation environment. You can call it a digital twin, you can call it something else, it doesn't matter. You need some environment with which your agent can interface. And sometimes the challenge on the environment is that people think they need the highest fidelity simulator, otherwise it's not worth it. I would argue against that. I think it really depends on the problem you're solving. And sometimes all you want to know is whether you should be choosing option A or option B, because you have a whole bunch of other constraints. And so in that case, maybe a simpler simulator is enough, for instance. So simulation is definitely a barrier.
Because if you spend too much time building a realistic simulator that can really realistically simulate complex physics and dynamics, then
you don't have time to do anything with it. And so I think on this front, I've been following very carefully what's happening in the field of offline reinforcement learning. Like, I think there's a lot of progress. We're not quite there yet. I think we still need a simulator currently, but the day we find better ways of doing offline reinforcement learning based on more traditional data inputs that most organizations already have, then I think that might unlock a lot of potential as well.
Which means I would suspect, Nic, we would need tutorials or how-tos so that people can learn how to get started, especially as you describe it. If I'm going to use RL, for example, offline on logs, right? So how do I do that? Give me a step-by-step tutorial so that I can get started, because it's too hard to glean any of these from papers.
Yes, no, absolutely. I think there's still a huge gap between the research papers and actually applying it. And some of that gap we tried to fill through the America's Cup use case we were just talking about earlier. But even, beyond just the pure simulation angle and the offline learning, I think there's still something around the amount of compute that's required usually for those problems to be solved. And look, while we see more and more sample efficient algorithms and the cost of compute is usually in a downward trend, I think it still remains a problem. RL remains a solution better suited to very valuable problems. So you want to be solving one big problem with RL. I'm comparing that, if you want, with maybe if you're in an organization and you're doing predictive maintenance, we have lots of small models on a lot of different parts in your organization that you just couldn't solve with RL currently because it's too fragmented. But if you have one big problem, and maybe it's AI-assisted design, like the product development use case we did for Team New Zealand, or complex operations or next best actions, then it can work. I think if you take a step back and think about what machine learning does, really, in many ways, you're making the underlying assumption that what happened in the past will happen again. Somewhere in your model, you have this stationarity assumption, and you're trying to capture behaviors that you hope will happen again. And that's why your model will be performing well. RL kind of helps you get away from that because it's much better at reacting to change. And that's why when you also mentioned trading as an application, absolutely. I used to work as a quant in hedge funds, and I'm sure that the same hedge fund now is probably doing RL for trading. Yeah. And so all those situations, I think, are well suited. But for me, a big challenge will still remain around also even if you solve all those problems, the change management and how you make sure that people trust the output of your RL model, I think will be absolutely essential, especially in situations where, as we mentioned earlier, results can be brittle sometimes, and in terms of how robust some of those optimizations can be. So it's not only more work on optimization and on algorithms, but definitely a lot more work on presenting the results and proving that this optimization is robust, for instance.
Yeah, I mean, last year when I wrote this article, so I listed some of these challenges that you are mentioning. This is great. So I said lack of detailed tutorials, being able to train offline, explainability and reproducibility, computational inefficiency. And the other thing, actually, Nic, which you folks may not have had to deal with because you were doing kind of a product design project, but now this topic of MLOps is a big topic. But can you imagine MLOps for RL?
Yes, I can. And we had to solve it at our small scale, because what we did was really putting RL in the hands of both designers.
I see.
And so we needed to solve a range of problems on that front. I've mentioned the compute aspect earlier, but I think beyond that, we obviously had to build all our infrastructure as code so that we could easily move our solution from our AWS environment into the client AWS environment, for instance. So everything was written as code. I think it's also then it becomes absolutely critical to really understand how your data is flowing through the system, making sure that the designers could actually use that system. And so really taking the lens of the end user and solving from their perspective what needs to be done here. The system we built in many ways is very, very quick iterations. And so it's different from maybe traditional machine learning, where maybe you train a model once and then you build in a system to monitor it, and you only retrain when you see the performance degrading, for instance. Here, because we were basically trying to rank different designs, we would actually train the system on all those different designs, find the best one, and then iterate again. So retraining is very much part of that life cycle, and so we didn't have to do anything that the client wouldn't already have been doing in many ways. But if I think about MLOps more broadly, in many ways we see MLOps as one of the key unlockers for AI to really scale in the enterprise. We see a lot of organizations who have spent a lot of time and effort building their first model, but the amount of time and effort they've put in their first model, there's no way that can scale within other areas. And so MLOps is really there to automate. And for me, it does four things. One is obviously increasing the productivity by enabling the teams to really focusing on the value-adding tasks as opposed to reinventing the wheel every time they build a model. And that's in line also with accelerating time to value. So you can build from pre-built blocks and really really focus on providing as much impact as possible as quickly. And then there's probably two more areas, one around sustainability and reliability. Like it's important to really understand when something goes wrong, where it went wrong and why, so that you save time trying to fix those problems. And I think more broadly, just around managing risk. For me, a lot of what MLOps does is around managing risk. It could be the risk of getting the wrong answer at the end, or the risk if the model doesn't run, for instance. In our case, like for the America's Cup, the risk was really about the system giving the wrong result, and therefore the team making the wrong design decision and ending up with a boat that wasn't as fast as it could have been. Luckily for us, they actually built arguably the fastest boat, and they actually won the competition. But so there's very different types of risk, but so it's very important upfront to identify what risks you're solving for.
By the way, there's another class of RL applications that I did not mention, but and it's mostly because it's mostly tech vendors who are doing this, although they are doing it for industrial companies. And this is the following, Nick, which is, it turns out, and I wasn't that aware of this, that a lot of these organizations already use simulation software from various vendors. And actually, if you look into the simulation software, some of the UI looks like a computer game, like here's a family or here's a retail store. And so if you once you see the UX, then you realize, oh, it makes sense that reinforcement learning can be plugged into the back end of this, just like it has been used to play some of these multiplayer games. So there are some companies who are doing this, and one company in particular, PatMind, based in San Francisco, also uses RLlib as their backend. So traditionally, the users of the simulation software will just use, as you said, traditional optimization models. But now with this backend, they are able to build richer and more complex simulations.
I agree, and I think I see a future where you might have almost RL as a service on your cloud provider. You might be familiar with Bonsai on Azure or other things like that. We're trying to get there. I think there's still a lot of limitations currently in terms of the type of algorithms or the type of simulators that are being supported. And I'm very optimistic about that line of that direction of travel. I think for what we did, it turned out to be so complex that we had to build a lot from scratch, but still keeping always in the back of our mind, like, let's make sure we don't reinvent the wheel, because that's our biggest failure mode. If you do a pre-mortem before a project, one huge thing is we spend too much time reinventing the wheel. And so here for us, when we used Ray, for instance, was really about understanding what we could do, at least with the version we had at the time, and how to then, we did spend quite a lot of time managing spot instances and making sure that our system on Ray could work well with spot instances. And a lot of it fundamentally comes down to how you save the state of your learning algorithm when you lose the node. And I would argue that when you think about that at the beginning, it might actually influence your choice of algorithm. Like how easy it is to stop and restart an algorithm would become a very important dimension in how you piece the whole thing together.
Now, do you think, Nick, that it might well be that if we look 5-10 years from now, that RL might actually be in a lot of these tools without actually, with very few teams understanding the details and just like I said in the simulation software, it could be that the people are building simulations and they don't know that it's RL.
I think, yes. And, like, even for what we did, like our end users at Team New Zealand didn't really understand RL, and they didn't need to. And that was the good thing. They were too busy with their own things. And you just bring RL as an enabler or as a tool to help someone do what they do best by enhancing the speed at which they can do it or giving them more options. So yes, I do see it as a really interesting future development. Obviously, there's still a lot of challenges to be addressed, but I think there's a lot of pull from industry and a lot of push from academia to really bring this into a world where it becomes a lot easier to use.
So while I have you here, I wanted to ask you, since you talk to a lot of enterprises, I wanted to ask you for your take on machine learning and data science in the enterprise in general. So we talked a little about MLOps. So what are some key challenges or on the positive side, trends that you're seeing? Because sometimes I find myself a bit in a bubble here in Silicon Valley.
So the view from, at least from my trenches, if you will, I mentioned MLOps obviously as a key unlocker to enable scale. But I guess before you get to scale, you need to first understand what AI can do for you. And so a lot of the challenges we see are organized.
Quick question. So do you find yourself still having to do kind of educational talks about?
Yes, I think educational talks are maybe not so much about just the value of AI. I think a lot of people now understand that, but it's more educational talks about how to go about it. It's like, okay, I want to do AI. Like, what should I do next? And so a lot of the challenges are
hire a data scientist.
Well, before that, I think you need to make sure that the use cases that you want to solve are obviously aligned with your strategy, and then only see AI as a tool to actually solve those use cases. And then obviously, when you talk about the enablers, yeah, absolutely, hiring data scientists, getting the right talent. And I think this talent will also shift over time as well. If you look at data engineering, data science, and other roles. We talked also
ML.
Yes.
Right. By the way, before we talked, I mentioned that I interacted a lot in the past with MGI, McKinsey Global Institute. A few years ago, they released a study about who's doing well in AI and machine learning. And I think one of the key findings was that the companies that are doing the best are the ones who have this foundational technology layer, right? So they already have BI and a data warehouse in place, and so now they can start doing ML and AI. And as you were talking, it just reminded me that we have now this resurgence of interest again in data pipelines, data quality, data infrastructure, and data engineering. And it seems like, to me, that seems like a great place for companies to invest is, let's get the basics down, and then we can always do ML, right?
You can. If I think about the four main enablers, I mean, I was mentioning talent.
Yeah.
Definitely that's one enabler. The other one is around technology, and we've talked a lot about the infrastructure. One is on data, and that's where obviously quite often any investment you make on data is what's going to have the most impact on the actual performance of your system. And the fourth enabler, just to mention it, is also about maybe the mindset and how you deliver very iteratively, as opposed to transforming everything in one go. And so just on data, just for a second, it's true that because AI relies so heavily on data, any investment you make on data is a prerequisite. one failure mode we see though sometimes is organizations who might spend 2 years just doing a data transformation without actually generating any value along the way. And so not only they're decommissioning systems and putting them into a new data warehouse, so they're preventing current use cases from executing because the old systems have been decommissioned, but the new ones aren't necessarily in place. And so there's quite a trade-off between how you innovate on the data side and how you make sure you still deliver value along the way. And so once you have the strategy, those 4 enablers, then the last thing you really need is around the change management and making sure that you build the right capabilities and the right workflows for that, so that people will actually trust and therefore use those systems. One big challenge sometimes is, for instance, to build a really fancy system, but you're just building one new screen for someone to look at. And then they will not look at that one new screen because they have too many screens, and therefore they will never use your system. So thinking right from the start about all those different aspects is really what helps organizations capture the most value from AI.
So where do you fall, Nick, in the centralized versus non-centralized ML and data capability? Centers of excellence versus,
yeah, look, it's a good debate. I think I would argue that what I've seen work is when an organization is starting, I think it's worth centralizing a lot of that function because they just don't have the scale. And the last thing you want to do is just hire one data scientist in your team because they'll feel alone and then they'll probably leave. So when you're starting, you really want to create that community in a centralized place. Then as you build more use cases, deliver more value and grow, then yes, then you want to be decentralizing some of those functions so that your data scientists, for instance, could become subject matter experts in specific business verticals, for instance. And then you only keep centrally maybe the functions that maybe you don't need at scale everywhere. Like it could be your, I don't know, enterprise AI architecture or other things, or very, very senior team members who are only there to unblock others, for instance. So it really depends on where you are on that journey. And I would also argue that it's not because you see another organization doing something one way that's necessarily what will work for you either. So there's also a lot of common sense and a lot of facts that you only as an organization know how to best make it work for you.
So we touched briefly on auto ML. So if auto ML, so if I have the right data, the MLOps, the pipelines, I've got a nice repeatable practice, then I won't need that many data scientists, right? So,
yeah, it's one view. I think what I've seen in practice.
I need more data engineers, maybe.
You do. I think there's definitely a trend for more data engineering. I think the data science job itself is changing because of AutoML tools actually becoming better. I think a few years ago, they just weren't up to scratch. So, but I think now they are getting better. But the risk I see is that then people relying too heavily on an AutoML platform to build their models. And then they're not aware of the trade-offs or the underlying assumptions. And sometimes some of those AutoML tools are very much close to the rest of the world as well. And so they force you to bring a lot more of your other tools to that platform to be used. And that, to me, is not necessarily a good thing. But there is definitely a trend to maybe turn AI projects more into just software engineering projects. And you have your AutoML part that does the modeling. I think some of the key differences still that people have to be aware of is that compared with traditional software, I think AI software is interestingly built on feedback loops. And the way you need to monitor and retrain. And right from the start that your model will degrade over time. And I think that's a fundamental difference compared to, I don't know, you're building an app and you have no expectation that your app will degrade over time. But with AI, you have that expectation, and therefore it's traditional software engineering with additional constraints on how you build all those feedback loops. And I think that's really where that MLOps part comes in.
No, I mean, I think that's exactly right. So it's almost like it's not like it's not like if you're developing an ML application, you won't benefit from reading books from application performance management or SRE. All of those ideas still help, but then, as you say, you need more. There's additional requirements, right? So one last topic: responsible AI. We talked about managing risk. A few years ago, when I was giving talks on this topic, I actually used that umbrella, managing risk. Uh, but now I think responsible AI is also a good umbrella. But to what extent, Nick, are these concerns around bias, security, privacy, safety, reliability? To what extent are companies concerned about this at this point, based on your conversations?
I think they should all be more aware. Some of them are already doing a lot. I think for me, when I first talked to an organization about AI and tried to gauge, if you want, the level of maturity, a simple question is, okay, well, what are you doing about trustworthy AI, for instance? If they say, oh yeah, we thought about it, we're doing this and that, I know they're already well ahead of probably most of the pack, because a lot of organizations are still fundamentally trying to get value out of AI and fundamentally just don't have the bandwidth to think about all those other consequences and at the same time. It also depends a lot on the type of activity the organization is doing. Obviously, if you're in a B2C world, you will be putting a lot of emphasis on fairness, on bias, and things like that. For instance, if you're a bank building a risk model for mortgages, or if you're a telecommunication company deciding what service to offer to your client. I would argue, though, that if you are, I don't know, a process engineering company, your concerns are very different. And you have situations where all you want is a system that works with the right framework around it, but you don't necessarily need to know all the details of how your system works. And that's typically where, for instance, going back to RL for a second, that's where I would put RL. Like, we found it extremely difficult to actually unpack all those things to really get a level of transparency, even on what our neural network deep inside that system was doing. But for what we're doing, that was okay.
That is a challenging and scary prospect, responsible RL.
Yes, it is. And I think as those new technologies mature, I think what's exciting for me is to see the new domains of application that they can be used for. So just one that jumps to mind on RL. We talked about the need for a simulation. Well, I think it was a few weeks ago, the European Commission announced a project called Destination Earth, where they will be building a very high precision digital model of the Earth, which will then unlock potential to do RL on the Earth model, for instance. To really enable more sustainable development and obviously ultimately support the new policies. But if you do have a digital model that's reliable and fine-grained enough, then potentially why not doing RL on that model of the Earth, for instance? So I think the prospects are really, really bright. But as everything to do with AI, I think you have to be very aware at the beginning of what the potential unintended consequences of what you're doing are. I'm not even talking about intended consequences here. You can do AI to do bad things. That's a totally different topic. But I think for a lot of practitioners, they just have to be much more aware about the unintended consequences of what AI can do.
Actually, so one of the things that, as you were talking, it struck me is, so one of the things that it seems like a lot more people are making sure they have tooling for is during the development process. These are the experiment tracking, experiment management tools. MLflow is an open source project, but there's other proprietary experiment management tools. So is that a Silicon Valley thing, or are you seeing that as well in regular companies?
No, look, it's definitely something that we see in more regular companies. I think it's part of that broader journey on scaling AI, and I would put that under that MLOps broader umbrella. If I have take a big, very broad definition of MLOps, like I would include those monitoring tools and model management tools, and even feature stores, and all those buckets of activities that can be automated or better organized and therefore controlled to enable AI.
Being traditional companies looking for solutions in these buckets?
Yeah, I think a lot of more traditional companies are realizing that they need to find solutions in those buckets to really fully unlock that potential. And, you know, like, as I was saying earlier, if you just do one model, sure, you don't need a feature store, you don't need a model management system or a way of doing champion challenger on your new models. But as you build more models, and you know, you can quickly scale to hundreds of models. If you don't have those tools in place, then you're actually increasing the risk to your organization as opposed to reducing it. So I think it becomes almost a forcing function to make sure that those different buckets are addressed with the right tools.
And by the way, if you don't have this repeatable, scalable, sustainable ML and AI practice, guess what? Your competitors will. And they'll be able to move faster.
They will, yes.
And with that, thank you, Nic. And for our listeners, as a reminder, Nic will be giving a keynote at the Race Summit, and you can find more details at racesummit.org. Thank you again, Nic.
Thank you, Ben.